Hi, everybody, and welcome to the second part dealing with the basically the geometry of the moon, the earth, and the sun. In the first part, basically what we found was the relative sizes, namely how big the moon is in comparison to the earth, how big the sun is in comparison to the earth, how far is the sun is from the earth in comparison to the size of the earth, how many radii, if you wish, of the earth, and also how far the moon is from the earth in the same measurements. Mr. Aristarchus basically found that the distance is about 70 times. We know it's about 60 times the moon is from the earth in terms of how big the earth is, in terms of its radius. And also, so everything was given in terms of one parameter. So if somehow we can measure, for example, the size of the earth, we should be able to tell the size of the moon. We should be able to tell the distance from the moon. We should be able to tell the size of the sun, and we should be able to tell also the distance from the sun. So all we need is one actual measurement. And this is exactly what Mr. Eratosthenes did in about a century later, around 200 BCE. This is exactly what he did. He was living in Alexandria, and he heard of a town in southern Egypt named Sion, where during one time of the year, namely the summer solstice, the sun does not cast any shadows. If you go there, for example, and look into a well, you will see the inside of the well, basically the bottom of the well. So the question is, he used that to his advantage, and he used the distance from Alexandria to that city. It's actually modern day Aswan, which is in southern Egypt near the big dam on the Nile River with the border of Sudan. So let me share with you the screen to show you exactly how he reasoned and found the actual size of the earth, namely the diameter or radius of the earth. First, he had to find the circumference. Once he did that, it's a simple geometry to find the actual radius. Let me share the screen. So imagine with me that this is the city where there is no shadow. It's modern day Aswan, okay? That's in southern Egypt, okay? So here, the sun rays, now he knew about also the measurements of that Mr. Aristarchus did, namely the fact that the sun is very far away from the earth, which means that the rays as they hit the earth, they all are parallel. So this ray and this ray, as they hit southern Egypt and Alexandria, they must be parallel. The one that does not cast any shadow must pass by the center of the earth, okay? The one that is that casts a shadow on the same day during the summer solstice, casts about 7 degrees in Alexandria, that must miss the center of the earth. It goes straight through the earth. Obviously, the blue lines in here, they're just to extend the actual ray of the sun. The ray of the sun does not penetrate the surface of the earth. So this is assumed to be the earth. Okay. You know that the shadow casts 7 degrees in here. There is a property of parallel lines. If you cut them with the same line, which is the red line in here, going from the center of the earth toward Alexandria, that line also makes 7 degrees in here too. This is a property of the parallel lines. If you have two parallel lines and you cut them with the same line, this angle and this angle are the same. As a matter of fact, this one also and this one also are the same angles. We don't care about those, all we care about the shadow in here, and that must be the same angle. Now, the angle of 7 degrees sustains the distance, the arc distance between Alexandria here and also Aswan in here. That distance nowadays is measured in kilometers, is roughly about 800 kilometers. In the old days, they use different measurements. They use actually how many stadii, how many stadiums basically, because that's a large enough distance to compare stuff with it. Anyway, let's take the 800 kilometers that we know today. It's about 800 kilometers, that distance. We know the angle is about 7 degrees. That's what the shadow is coming from Alexandria, and that's this angle that sustains that arc distance. Well, then he reasoned the earth must be spherical. He knew also that from Aristotle and the people before him. So all he needed was to argue the following, that the ratio of the entire angle going from the beginning to the end, which is 360 degrees, that ratio of 360 degrees over the angle that sustained the arc distance, which is 7 degrees, must be, this is plane geometry, by the way, must be the same ratio of the entire circumference. If I were to go from any point, it doesn't matter where I start from. If I go from this point and go through the entire planet and come back to the same point, not to look anywhere else and come back, that is the circumference of the Earth, okay? So the circumference in here of the Earth, that's what we don't know, divided by, we know this distance from the, in Egypt, how big that is, that's about 800 kilometers. This ratio is roughly 50. It's actually 51 something, so let's kind of put it 50. So the circumference from here becomes a simple algebra. All I have to do is multiply by 800 times 50. And that should give me about 40,000 kilometers in circumference for the Earth. So this is the circumference of the Earth, okay? That's his reasoning. About 40,000 kilometers. Then from here, I can find the radius of this, of the Earth. It doesn't matter where I take it. If I take this is the radius R, so this is the radius of the Earth. The radius of the Earth then multiplied by 2 pi should give me the circumference, the 40,000. Well, I have everything. I know what pi is, it's 3.14. I know what 2 is. From here, I can find the radius of the Earth, which is 40,000 divided by 2 pi. And that is roughly, I'm estimating it, to about 6,400 kilometers. So we know the radius of the Earth. Actually, it's slightly less, but I'm just giving a rough number in here. So, but it's very close from the correct value. That's amazing. This is 200 years BCE, way long time ago. Okay, 2 centuries before that, so it's 2,200 years ago when they measured the radius of the Earth based on these observations. Since we know now the radius of the Earth, namely how big the Earth is, we should be able to find how far the moon is. Remember, the moon, according to the reasoning of Aristarchus, was about travels on the path of the Earth about, it makes 220 times basically Earths. That's the path of the moon as it goes around. So that's the circumference of the moon. So if this is the Earth, make 220 times the size of the Earth, that should give you the path of the moon. From here, he deduced that the moon must be about 70 times the radius of the Earth. So this is the distance, the Earth to the moon, Earth, moon. That's 70 times this radius, and the radius is 6,400. Obviously, this is an overestimate. We know the actual number is about 60 times 6,400. So his measurements, the measurements of Aristarchus, should be, let me pull a calculator in here quickly and do the algebra because I never done it. So it's not 71 times, what is the times? 6,400. Okay, so it gives me 448,000 kilometers. 448,000 kilometers. That's the estimates then. But we know today that this is a more accurate number. It's 384,000 kilometers. It's not too far, actually. I know you're saying, oh, it's a lot, but it's really close enough if you do the ratio. This is close from 400,000. This is close from 400,000, and both of them are within the same range. Kilometers, okay? And I know in miles it's slightly less, but still the same distance. So the point being in here, now once we find the radius of the Earth, we can find anything then after that. We can find the distance to the moon, we can find the size of the moon. All I have to do for the size of the moon is divide this number roughly by 3, and that should give me the radius of the moon and so on and so forth. So we have all the information we need now based on this observation. This is Mr. Eratosthenes who did this. Eratosthenes. Okay, roughly about 200 BCE, before the Common Era, or the so this is basically when we have these measurements. So it's all great, okay? This is for the moon. How about other objects? We really, if I go to the moon, if I go tonight, for example, and observe the moon, what I can do is take a ruler with me, and try this at home if you wish. take a ruler, okay, and move the ruler a certain distance away from you and measure the size of the moon, okay? My camera is adjusting in here. Measure the size of the moon, how big the moon is. If you measure the ruler to about 17.5 centimeters, 17.5 centimeters is roughly this much, okay? So if you measure that distance and measure the size of the moon, you should find the moon roughly in diameter, about 1.5 millimeter. So let me share the screen again. So imagine we did this. Imagine we went outside and used this. So the ruler is about 17.5 17.2 millimeters, about 17.2 centimeters. That's about 172 millimeters. The moon, the entire moon, I don't mean just the radius. I mean the entire moon, the size from top to bottom. Call this L. Actually, this is the diameter of the moon. This should be about 1.5 millimeter. Okay, slightly over a tenth of a centimeter. Okay, so this distance in here, this is what we call the angular size of the moon. So this is the angular size of the moon. And it's an angle. Okay, how do we find angles? From plane geometry. If this were a right angle triangle, this would be the hypotenuse, this would be the opposite, this would be the adjacent, and the tangent of an angle is going to be equal to the ratio of the opposite over the adjacent. Well, in this case, it's simply equal to 1.5 millimeter. That's why I have to use a millimeter instead to cancel the millimeters, over 172 millimeters. Cancel the millimeters, and we get the angle extremely small in radians. Okay, there is something in trig that is called the small angle approximation. When the angle is very small, its tangent and its sine are equal to the angle itself. Okay, provided it's in radians. We don't really use radians on a daily basis. We use degrees. And a degree, there is a simple conversion from a radians to a degree, and that involves 2 pi. 2 pi is 360 degrees, okay? So that is full circle is 2 pi, and that is also 360 degrees. So all I do is measure the angles in degrees, then I have to refer them to this degree measurement in here. And this is what we'll end up with. Imagine that you have an object far away. Mars or Jupiter or whatever planet that you're looking, or whatever star that you're looking at. So in this case, it's the small angle approximation would work perfectly because this distance is extremely large. Okay, so this is the distance to the object that you're looking at. Okay, so this is on a big, I mean, imagine that there is a huge circle where that object is, and I'm trying to understand in here, or trying to measure the angular size of that object. I call that alpha. Okay, I call that alpha. This big circle in here has a radius d, so its perimeter or its circumference is actually 2 pi times d. So this is the circumference of that big thing. But all I'm looking at in here is just this size of the object, which usually we refer to as L. That is actually the diameter if the object is spherical. Most of the objects that we look at are spherical. We cannot see anything that is not a planet or a star far away, I mean, with a naked eye, unless close enough for us. Anyway, so in this case, what I can say is the ratio of this size L over the entire circumference, which is 2 pi times d. Remember, the object is d away from us in whatever units that you're using, is the same ratio as the angle alpha measured in degrees over 360 degrees, because that's how it takes to go from the entire circle to find that circumference. That's 360 degrees, but I didn't go that. I want only alpha in here, okay? Alpha in degrees to find this arc distance, which is L, and it divided by the same circumference. From here, I have a measurement, I have a formula, if you wish, that gives me the size of the object L in terms of how far it is. So if I know how far it is, and if somehow I can measure its angular size, this is called the angular size, divided by 360, then I'm in business, provided that this angular size is measured also in degrees, okay? Then this is how far it is. This is the distance to the object, and this is the size of the object. So this is a useful formula to use to find how big the objects are, if I can somehow measure this angular size. So this is basically the trick behind this formula. This is what we need to do. Okay, usually either you find the size in terms of the distance, or we can do the opposite. We can find actually the distance if I know somehow the size. If I somehow determine the size of an object, all I have to do is just do simple algebra in here, move the d, move everything to the other side. It's going to be 360 times L divided by 2 pi times alpha. So it's going to be L divided by 2 pi times 360 in degrees divided by alpha, which is also must be in degrees. So in other words, if I measure the angular size of the object, and if I know its size, I can find how far it is. So this is the same formula. Either you write it in this way, or you write it in this way, it's the same thing. This is only true only for small angles. Okay, again, I'm using some trick stuff in here. I'm sorry, this is true. Yeah, it's actually based on the tangents in here. Anyway, so the point being in here is, because these two sides in here, when d is very large, are assumed to be very close from one another. As a matter of fact, they should be the same size, okay? Otherwise, there is a tilt to the object if it becomes close enough, and we really have to use that trig identities. I mean, if you use this formula, for example, for a building, and you want to find, or a pole, for example, next to you, and you want to find how tall it is, and you were somehow, so if you know how the distance in here, d, and you would want to find how big the object is in this case, obviously this length and this length are not the same. So this is going to be the adjacent. If you somehow can measure this angle, of course, this will be your angle. So if you can measure that angle, then in this case, you can find how high the object is, like a pole. But you have to use trig in this case. You cannot use the small angle formula. You have to use the tangent in this case. If you know the angle, you can find its tangent alpha, and tangent should be exactly the ratio of h over d. In other words, from here, you can find how high an object is, which is d times the tangent of alpha. So you can use that. So this is the more accurate formula, if you wish, for all angles. But since the objects that we're dealing with in astronomy most of the times are very, very far away in such a way that d is much, much bigger than L, then in this case, this formula works. So it's actually small angle approximation, but it works. I mean, for Jupiter, or for even the moon, or which is the closest object, about 384,000 kilometers from us, this should work beautifully, okay, for us. It should give us all of the values. As a matter of fact, we can apply it for the moon, since we know all of these values. Again, for the moon, I just found that this ratio, alpha, is about 1.5 millimeter divided by 172 millimeter. The problem with this formula in here, the way that I wrote it, is, again, the angle has to be in degrees. I mean, in radians, the way that it's written, the way it is. So I need to convert it to degrees. For that, I multiply the number by 180 degree, or 360 if you like, 360 degrees, and divided by 2 pi, okay, which is 2.314. So if I do the math in here, again, 360 divided by 172 times 2 times 3.4 times 1.5. If you do the math, you're going to find roughly about half a degree, okay, half a degree for the moon. And that's exactly how much it should be, because then you can use this formula to find its size. You can find that 384,000 versus the 1/3 of 6,400 is satisfied if I put it here, 0.5, half, okay? Everything should work out the same, and it should work. And I think this is part of a homework assignment anyway, to check the formula for the moon, and actually also calculated for objects such as Jupiter and other objects in the sky. Okay, there is a problem in here with the angular size, and that problem is what is known as the moon illusion. Let me explain what that is. If you go early at night and look at the moon, and let's say, for example, it's on the horizon, okay? The horizon has mountains and hills and trees and all kinds of things that you're looking at. The moon appears to be one side. If you look at it in the middle of the sky, it appears smaller in size. 3 from those objects in here. And if again, it's back into the horizon, again, it appears bigger because you have the mountains, you have the trees, and you have the houses, whatever is on that side, okay? And this is what we call the moon illusion, because of the fact that this is your brain is adjusting. Your brain knows, for example, that the size of this mountains is big and the size of trees is big. So it adjusts the size of the moon to reflect that those big sizes and gives it actually a bigger size than what it should be. Whereas in here, it's free from those objects and there are nothing in it. So it's going to give you another value for it. Your brain makes another adjustment in here. So this is what we call an illusion in this case, because it's not real. As a matter of fact, the moon is closer to us when it's immediately in our zenith than when it's in the horizons, because of the fact that the Earth is spherical shape. At some point, if I'm here, at some point, it's twice the radius of the Earth. And in here, it's about the radius of the Earth. This is just when I can see it in here. And in here, it's nothing. So this distance is reduced. So the moon is actually closer to us in here than anything, especially these 2 points, by 6,400 kilometers. Okay. So it should appear bigger, but it is not. And that is because of this illusion. The book has a nice picture for you guys. Let me stop sharing this point in here. And what I did with that picture, I used something called GIMP, which adjusts basically the size of the, which you can edit pictures with. And what I did was I removed the background. Once I removed the background, there are 3 objects in here. Let me share with you what I'm talking about in here. So what you're looking at in here, you have 3 spherical objects that represents the moon. Obviously, they all are the same. If I put back the background now, this is what the picture of the book is. This one on the bottom appears smaller than the other 2, and that is because of the rails. The brain knows how big the rails are or how far apart the 2 sides of the rail are. So it adjusts for that size when you look at it at far distance. So this object in here appears bigger than the separation. The brain makes it bigger than when it's up close to you. And this is actually a trick. Your brain is being tricked actually by the scenery, by what is next to it. But as you can, from here, this one is smaller than the other 2, but actually they are all the same size. So this is what we call the moon illusion. So when you're doing measurements, for example, for angular sizes, do not be tempted from the first observations to think that, oh, that object is bigger than this one just from first sight, because probably it's near something, okay? So you have to actually do the measurements to find how big the angular size is. And again, use a formula to find how far the objects and how big they are and things like that. Thank you.